So we have looked at the preparation of alcohols from ketones, aldehydes, and carboxylic acids using a mix, either lithium aluminum hydride for carboxylic acids and sodium borohydride for ketones and aldehydes to the corresponding alcohols. Now let's talk about the preparation of diols. Diols are named using the same method as alcohols, if you remember. For instance, this will be 1,3-propane diol or propane 1,3 diol. This will be 1,5-hexane diol or hexane 1,5 diol. Now, if two carbonyl groups are present and enough moles of reducing agent are added, both can be used, as you can see here. If you use hydrogen over palladium, you get the diol from heptane 2,6 dione, or if you use lithium aluminum hydride, you get the diol as well. And if you use sodium borohydride, you get the diol as well. Now, recall that we looked at the preparation of diols in chapter 9, beginning with an alkene. And now you know that with the alkene, we use MCPBA, a per acid, followed by acid hydrolysis. Excuse me, you get the anti-dihydrogenation. But if you use osmium tetroxide followed by NMO or sodium hydrogen sulfite water, you get the syn dihydrogenation, the syn 1,2 diol. So these are things you need to do, you should be well aware of now. Now, Grignard reagents are often used in the synthesis of alcohols. To form a Grignard, an alkyl halide is treated with magnesium metal. That's basically how you form a Grignard. And the good thing about the Grignard is that you convert an electrophilic carbon to a nucleophilic carbon, you see. And that is evidenced in the change in the oxidation number. Ordinarily, we expect that the oxidation number of carbon will be +1, while of carbon here will be -1, right? So you can see here, this is a reduction has happened. A reduction has happened. See, this is a reduction. You see, you've gone from the carbon here, which is -1, to the carbon here, which is -3. You see, that is a reduction. You see, that you have a reduction has occurred. The reduction has occurred because if you look at this carbon here, ordinarily carbon is 4. Now you have 1, 2, 3, 4, 5, 6, 7, -7, and that is positive, and that's I said -3. So you get -3 here, while here is 4 minus 5, which is -1. You see? So that's a Grignard for you. A Grignard reagent prepares a reducing agent. Prepares a reducing agent. Now the electronegativity difference between carbon and magnesium is significant, so it has a lot of ionic character. Okay, the carbon atom is not able to effectively stabilize the negative charge it carries, and so as a result, it's going to want to act like a base. It's going to want to act like a base as well as a nucleophile. So Grignards are great bases, and also they're great nucleophiles, right? And that's why you don't want to bring a Grignard in contact with water. It could act as an acid, and you have the preparation, the formation of an alkane, and the formation of the magnesium hydroxybromide. Now, if the Grignard reagent reacts with a carbonyl compound, an alcohol can result. See? So you can see here, the Grignard acts as a nucleophile and attacks the carbonyl, and upon proton transfer, it gets the tertiary alcohol. So you start out with a ketone, and you get the tertiary alcohol. The reason is because you have added an R group. Note the similarity between the Grignard and the lithium aluminum hydride mechanism. Because the Grignard is both a strong base and a strong nucleophile, care must be taken to protect it from the exposure of water. So you cannot bring a Grignard close to water or moisture. The reason is because the reaction is heavily favored. As you can see that if you bring it close to water with a pK of 18.7, you form the alkane which has a pK of 50. And we learned in Chem 12a that the reaction always favors the weaker acid. And so you know that this reaction will go without any problem. See? And so if water can be used as a solvent, the best solvent to use will be a polar aprotic solvent. We learned about polar aprotic solvent when we were looking at SN2 reactions. Polar aprotic solvents include things like ethers, right? Ethers are great polar aprotic solvents, like diether ether or any of the ethers, right? Now, we also have things like DMSO, say DMF. All these are examples of polar aprotic solvents. Now, what techniques do we use to keep atmospheric moisture out of the reaction? You know, if you don't want moisture in the system, you need to use what we call vacuum sealing techniques. I'm not going to go into detail, but that's something that we use in organometallics to preserve the integrity of organometallic reagents. And typically how an organometallic reagent is formed, just like I showed you earlier, is the fact that you have an alkyl bromide and then you have magnesium inserted in between the carbon-bromine bond. And so you have ended up transforming an electrophilic carbon to a nucleophilic carbon, which serves as both a nucleophile and a base. See? So Grignard acts as both nucleophiles and also act as great bases. Now, if you started with a ketone, like we saw in an earlier example, you can get a tertiary alcohol, right? And if you start out with an ester, if you use an excess of a Grignard, you end up with the tertiary alcohol. With an ester substrate, excess Grignard is required. Why? Because you are delivering two of the alkyl groups. Now, list some functional groups that are not compatible with Grignard. Any functional group that has an ionizable proton, right, like a hydroxy, an amino group, or maybe a carboxylic acid, will destroy a Grignard because the Grignard acts like a base. So if you bring an acid next to a Grignard, they are going to destroy the Grignard, and so you can't afford to bring any reagents that have the following, either a hydroxy, amino, or carboxylic acid, or any functional group, generally with those with ionizable protons. So if you have an ionizable proton, of course, you have to make sure it's protected. Okay. Now, if you are going to design a synthesis for the following molecule, starting from the alkyl halide, right, and the carbonyl, right, you can easily see that this is where the attachment occurs, and that means here this was a ketone prior to the reaction, and this other bond was the Grignard. This is what Grignard, and this was the ketone. On the other hand, you can see where the attachment occurred. You see, the attachment could have occurred here, or it could have occurred here. Any of those would have been acceptable. If it occurs here, right, then that means that this will be what we began with. But if it occurs here, right, that means this is what we had prior. See? And so that's basically how you're going to look at it. You just have to do some examples. Now, protection of alcohols. If you consider the example below, why won't this work? This will not work because you have an ionizable proton. This is an ionizable. It's an ionizable proton, right? An ionizable proton. And so we know that that will not work because it will kill your Grignard. You see? If you want this to react with this, nothing will happen. The alcohol can act as an acid, especially in the presence of a reactive reagent like a Grignard. So to prevent this, you have to protect your alcohol. And a great way to protect alcohols is by converting them to a very stable molecule by introducing something like a trimethyl silyl chloride. See, so you protect it. So once this alcohol is protected, right, you can now make the alcohol, you can now make this group, you can now make it to a grignard, and you can do all your chemistry, and after that you can protect. Now let's look at a classic example. Now, one of such protecting groups is trimethyl TMS. Now basically what you do in TMS is you convert the OH group here to a very bad leaving group, and the bad leaving group is trimethyl ether, or OTMS. Now the TMS protection step requires the presence of a base, and if you can propose a mechanism which is very straightforward, you can actually practice that on your own. You can see that the OH here, the hydrogen here, has been converted to a TMS there. And to be able to, this evidence suggests that the substitution of the silicon atom occurs by an SN2 mechanism. Because Si is much lighter than C, it is more open to backside attack. See, this is unlike carbon. If this were carbon, of course you know that SN2 would be impossible. SN2 will not happen. But because it is a silicon, because this is silicon, SN2 becomes possible. See, so the attack, see, of the OH, the oxygen from the backside, is what makes the reaction. You see, so TMS can later be removed by either acid or TBAF, which is tributyl ammonium fluoride. There's something you're going to supply the fluoride ions. So to protect protection of alcohol, so you can see here, the OH group here is protected using trimethyl chloride in the presence of base. So once the OTMS has been placed, you can now convert this into your grignard. Once the grignard is made, then you can now make it react with the ketone, and you get the tertiary alcohol in the process, and then you deprotect, and you get the formation of your tertiary alcohol. You see? So basically that is what is happening. Now, phenols. Phenols are very interesting. 2 million tons of phenols is produced industrially yearly. And how they produce phenols is by benzene, with the reaction of benzene with propene, right? And to give cumin, and then cumin undergoes an auto-oxidation, to give the peroxide, and then phenol and acetone. And of course acetone is a very useful byproduct. You know, phenol is a precursor in many chemical synthesis, especially in pharmaceuticals, polymers, adhesives, and food preservatives. Now recall that this reaction from section 7.5, we know that we can convert a tertiary alcohol in the presence of acid via an SN1 reaction to give the corresponding tertiary alkyl bromide. For primary alcohols, the reaction occurs by SN2, right? And we can use either an acid, right, and in the presence of course, a polar aprotic solvent, right? So these are things that you need to be well aware of. See, you need to be well aware of these things. You know, when you are trying to, when we're considering the reactions of alcohol, they will undergo SN1 with tertiary alcohols, and while they will undergo SN2 with primary and secondary. Okay. Now, let us stop here and we'll continue from here shortly.